our lesson for 2-7 linear quadratic systems. As you can see for this one, we are now going to be doing the explore and reason. We're just going to jump right into the lesson. And there are a few things that I'm going to be skipping from this lesson that you can read over either in the textbook or in the PDF notes, but there's just a few things I want to highlight from this lesson. So we have our essential question: how can you solve a system of two equations or inequalities? We're actually not doing the inequality portion here, in which one is linear and one is quadratic. So we're going to look at this example first. This one says, how many solutions does the system below have? So we're going to graph both of these equations and see where they cross. So for the top one, we have y equals x squared. That is the parent function. So the order of pairs that go along with that are going to be -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. And again, those are the same ordered pairs that we've been using pretty much the whole year. So then we have the second one, y equals 2x. This is a linear function. It has a y-intercept of 0 and a slope of 2. So I'm going to start at 0. You can see that is one of the solutions that we have. Then we go up 2 over 1, up 2 over 1, and I could keep doing that to give me enough to get a good picture. So this actually crosses in two different places. It crosses there and it crosses there. So the solutions to the system are 0, 0 and 2, 4. It crosses at two different places. Part B, which I'm actually going to skip over, has this equation. Instead of just 2x, it has 2x plus b. And it wants you to look at different b values and how that would affect the amount of solutions that you have. For example, if we move this entire equation down 1, if we go up 2 over 1, that I'm talking the linear here, so if I make it a -1, up 2 over 1, up 2 over 1, up 2 over 1, we would actually only touch the system at one place, so it would have one solution. And if I move it anything below that, so if I make the b like -2 or -3, it wouldn't cross anywhere, so it would have no solutions. So that is something interesting. You can look over just how changing, if there was a b on the end instead of 0, how that would affect how the linear and the quadratic interact. So that's this system, this equation. We're actually going to skip that for right now. So example 2, how can you use substitution to solve the system? Substitution is going to be your best bet because you are dealing with things that, because these are linear quadratic, one of your equations is going to be quadratic, one is going to be linear. They're not necessarily going to have the same number of terms in them, but substituting does take care of this. Since y is equal to this entire equation here, I can replace this y with 3x squared plus 3x minus 5. And that's what I'm going to do right here. So we have 2x minus the quantity 3x squared plus 3x minus 5, and then that's equal to 3. So we plug it in. Again, we're replacing the y with the 3x squared plus 3x minus 5. I do have to distribute the minus. Notice that goes to everything. And then I can combine my terms. I didn't move the 3 over because it looks like I'm going to have to either factor or use the quadratic formula here. And I do like to keep my square term positive, so I'm actually going to move all 3 of those terms over to the right-hand side just to make this a little bit easier to work with. So I'm going to be subtracting the 5, so that will make that a -2. You can do the quadratic formula here, but actually, now that I'm looking at this, this does factor. So I'm trying to make a positive 1, so I don't want to multiply the 3 by the 2, I want to multiply the 3 by the 1, and I want that to be a positive, so I want the 3 to be positive and the 2 to be negative. This gives me 3x minus 2x. That's going to give me my positive 1x. You could use the quadratic formula at this point. If you did the quadratic formula, you would still get the same two correct answers, which are 2/3 and -1. So even if you did the quadratic formula, your answer should still be the same as what we have here. So now, to solve the system, you have to have an x and a y value. We have two different x's here because this system actually crosses in two different places. If we were to solve this equation for y and graph both of those, you would be able to see where those two places are. But I actually have to go through and I have to plug both of those back in. Because the way we did the substitution, I have to plug them into the top equation. So if I plug in 2/3 into number 1, I have y equals 3 times 2/3 squared plus 3 times 2/3 minus 5. This might be a little bit difficult for you to do in your head, so you can use a calculator. Make sure you use one, though, that will do fractions, because if you use decimals, you're going to be cutting off part of your answer. Just like I left this as 2/3, I didn't say it was 0.67. You don't want to round those decimals that have fraction equivalents. So whenever you solve this, you actually end up getting -5/3, which means our ordered pair is 2/3, -5/3. So now when we plug in -1 into number 1, we get y equals 3 times -1 squared plus 3 times -1 and then minus 5. This is going to be a little bit easier to work with. This is going to be a -3 minus 3 minus, I'm sorry, not -3, positive 3 minus 3, and then minus 5 is going to give you -5. So -1, -5 is going to be your solution there. And you can plug both of those points into both of the original equations, and they should both equal out so that the left and the right sides are congruent. This equation, or this problem, I'm actually going to skip, but I do want to talk about it a little bit because the math, again, is in your textbook, and it is in the PDF notes that are in Schoology. So you have Andrew, he's kicking a ball up a hill for his dog to chase. The hill's modeled by this line through the origin. Move that down a little bit. It says the path of the ball is modeled by the quadratic. How far does the ball travel horizontally? So this actually wants to know a distance. We want to know how far it is traveling horizontally. I'm looking for this value. But in order, and then it says how far must the dog run uphill to catch it. So how far does it travel horizontally? That's what I've underlined in blue. So basically, that would be once you find the two places where your lines intersect, that would be the difference between the x values there. And it says how far must the dog run uphill? That's going to be this distance. And you could use the distance formula to solve that, or you could look at this using a Pythagorean theorem type relationship. So at least for the setup, to figure out the distance between the blues, I need to figure out where the parabola and the line intersect. And you can see here you have these two equations. You can actually just set these equal. So we can say 0.5x is equal to -0.5, not 0.5. -0.5x squared plus 6x. And then you could go through and solve this with the quadratic formula. And then once you get the solution of this, you would figure out how far apart your x values are. That would be the distance. And then going up the hill, then you would want to think about, if you look at the difference in your y's, that would give you the height. The blue line is how far apart the x's are, and then you could do Pythagorean theorem. Or you could do the distance formula, because the distance formula is basically Pythagorean theorem, but with the x and the y values separated out. So I did just want to talk through that briefly so you guys could see how that would be solved. The last thing I want to look at, we're not going to do this one either. Solve the equation x squared plus 9x minus 5 equals 4 minus 3x by writing a linear quadratic system and using the intersection feature of a graphing calculator. So this is what we did already, I think, back in topic 1. So you would want to make the one side x squared plus 9x minus 5, and then the other side, you're going to be looking at your 4 minus 3x, and then you would graph those and see where they cross. And this would be a perfect problem to use with Desmos, where you could just type in the equations and it would give you back your answers. So look this over. This wasn't a very long section, but this does wrap up our topic 2. So we'll be doing just a tiny bit of practice on this just to get you guys used to using the systems, and then you can look for the review and then the test on topic 2 coming up in the near future. So look this over. Go through the examples, go through the textbook if you're not quite sure about my explanation, and reach out to me if you have any questions.